Inside every single device we own, there's this invisible war being fought constantly. It's a battle against an enemy that we create every time we tap a screen or launch an app. And it's a battle that really defines the future of all our tech.
I mean, think about it, right? We want our phones to be thinner, our laptops to be way faster, our gaming consoles to be more powerful than ever. Every new generation of technology has to be a step up. But this constant demand for more, well, it creates a huge problem.
And that problem really comes down to a basic law of physics. Every single one of these amazing gadgets, from the tiniest chip to a massive data center, is fighting the exact same relentless enemy. Yep, that enemy is heat. As our processors get more and more powerful, they just get hotter. So keeping them cool isn't just some minor detail, it is the main challenge that's holding back the next big leap in technology. So that begs the question, are we really fighting this war in the smartest way possible?
To really get where we're going, we first have to take a look at where we've been. For years, the whole approach to cooling has been, well, kind of like brute force, using structures that come with some pretty serious downsides.
So here are some of the classic contenders you'd find inside high-end electronics. You've got things like pin-fin arrays, they kind of look like a bed of nails, or these really complex microchannels. But for this explainer, we're going to zero in on one that's super interesting: metal foams. The key word to understand here is stochastic. Now, it sounds fancy, but it just means something that's random and chaotic. And that perfectly describes the inside of a metal foam. Just imagine trying to push water through a super dense, tangled forest. That's pretty much what a cooling fluid is up against.
And that whole tangled forest thing creates a major trade-off. See, on one hand, all those random branches give you a massive surface area, which is awesome for pulling heat away. But on the other hand, it takes a ton of force, what engineers call pressure drop, to shove the cooling fluid through all that chaos. It's just not very efficient. And because it's so random, you get hot spots, which is the last thing you want on a sensitive computer chip.
And this brings us to the big question. If all that randomness and chaos is inefficient, what if we tried the complete opposite? What if we brought a little order to the whole cooling game? And that's exactly what this research did. Instead of that tangled forest, these researchers developed a totally new design based on a highly organized repeating pattern, a cellular structure engineered for maximum efficiency. The technical term for this is a periodic structure. It's the direct opposite of stochastic. So think of it like this. We're replacing that chaotic forest with a perfectly planned city grid. All the paths are clear, the flow is predictable, and everything is there for a reason. And this just shows the idea perfectly. On the left, you've got the clean computer model, that organized grid of channels and tiny holes. And then on the right, you see the real deal, precision machined out of a block of copper. But, a great design is one thing. Now they had to prove it actually worked.
Right, because a cool idea on a computer screen is one thing. But proving it works in the real world, that's everything. So the researchers had to test this new design both virtually and physically to see if the theory was going to hold up.
Okay, so first up, the simulation. This is basically a digital heat map showing what the computer predicts will happen. See that cool 22 degrees Celsius water coming in on one side? That's the blue and green area. As it zips through the grid, it soaks up heat from the base, and you can see it warming up into the yellow and red zones as it heads for the exit. It's a perfect digital forecast. But would it actually work that way? To find out, the team built this physical test setup. Now, it might look a little complicated, but its job was actually pretty simple. Just recreate the exact same conditions from the simulation and measure the results with insane precision. The process was pretty straightforward, but you had to get it exactly right. First, they blasted the base with 345 watts of heat to act like a super powerful processor. Second, they pumped distilled water through the new structure. And third, they used these ultra-sensitive thermometers to measure the base temperature and see just how well the new design was doing its job. So this is the moment of truth. After all the theory, all the design, all the building, did the organized periodic structure actually do better than the old ways? Did the city grid beat the tangled forest? Well, the very first result was a huge validation for the team. The blue line here is the computer's prediction, and the red line is what they actually measured in the lab. Look how close they are. They were off by less than 9%, which is incredible, and it proved their science was totally sound. And here it is, the headline number, Even under that blistering 345-watt heat load, the base of the chip leveled off at just 32.3 degrees Celsius. That's barely warmer than a hot summer day.
But how good is that, really? Well, let's put it into context. A previous study on an older pin-fin-style cooler under pretty similar conditions only got the temperature down to 40.5 degrees. This new design is over 8 degrees cooler. In the world of thermal management, that is a massive leap forward.
So this is way more than just some interesting lab result. A breakthrough like this in cooling has direct consequences for the kind of tech you and I will be using in the very near future.
So why does this matter so much? Well, because when you can pull heat away this efficiently, you can finally unlock processors that were just too hot to handle before. You can design smaller, more compact devices because the cooling system doesn't need to be so huge. And you make the electronics last a lot longer by getting rid of those damaging hotspots.
And just like the researchers themselves say, keeping the temperature uniform across the whole chip is absolutely critical. It isn't just about being cool, it's about being evenly cool. That stability is the secret sauce that gives us the reliability and speed we expect from our computers. It really makes you think, doesn't it? For so long, heat has been the bad guy, the big thing limiting our technological dreams. But as we get smarter and more organized in how we deal with it, you gotta ask, once we truly master heat, what's next? What kind of currently impossible technologies will suddenly be right around the corner?